congratulate to Dr. Anil Joseph, the IGS President, for being elected as a ISSMG Asia Vice President. We are really proud of you for the victory in the position. Now I would like to welcome the IGS President, Dr. Anil Joseph, SLGS President, Engineer Kailash Sahabandhu, NGS President, Professor Dr. Indra Prasad Acharya, Chair of 𝐿GEO 2024 and immediate past President of Nepal Geotechnical Society, Dr. Mandeep Subedi, and today's distinguished speakers, Dr. Sanchitha Jayakody from Sri Lanka and Dr. Sunil Poudyal from Nepal, respective issue members from the both host organization, esteemed participants from different part of the world to this special webinar, jointly organized by Nepal Geotechnical Society and Sri Lankan Geotechnical Society. NGS has been conducting a joint webinar series since 2024 with geotechnical member societies across the South Asia, following the formation of this Association of Geotechnical Society of South Asia, AGSSA. And the first webinar in this series was successfully organized in collaboration with the Indian Geotechnical Society, IGS, and following the success of inaugural webinar, the tradition of the knowledge sharing and the cooperation among South Asian geotechnical societies continues. And this time, the NGS and the Sri Lankan Geotechnical Society are teaming up for this special webinar entitled South Asian Collaboration for Geotechnical Excellence. The two eminent geotechnical engineers representing NGS and SLGS will deliver the lecture. Before we proceed, I would like to introduce today's program and the speaker briefly. We'll be here about nearly 1.5 hours. This webinar is composed of opening remarks from President of NGS, along with the introduction of NGS briefly. And after that, there's the opening remarks from the President of IGS, Dr. Anil Joseph. After that, we have the two invited presentation, Q&A session, invitation from the chair of 𝐿GEO 2027 to all participants to 𝐿GEO. And finally, the introduction to SLGS with the closing remarks by SLGS President. Then I would like to thank to Darshan Babu Adhikari, Secretary of NGS, Rajan Kesi, the Youth Convener of 𝐿GEO 2027, and Engineer Bipul Mainali, the Youth Coordinator of NGS, and other NGS member for their technical support for today's program. With this note, I would like to request Professor Dr. Indra Prasad Acharya, the President of Nepal Geotechnical Society, to deliver his opening remarks together with the short introduction of a Nepal Geotechnical Society. Over to you, Professor Acharya.
Oh, thank you, Dr. Pathak. Welcome to all panelists and attendees for the today's webinar. Dear executive members from Nepal Geotechnical Society and Sri Lankan Geotechnical Society, and all the geotechnical professors. First, I would like to congratulate Dr. Anil Joseph for being elected as a Vice President of ISSMG for Asia. We are Nepal Geotechnical Society is very proud in this issue. Congratulations, Dr. Anil. This is a joint webinar series, South Asian Collaboration for Geotechnical Excellences. The Nepal Geotechnical Society and the Sri Lankan Geotechnical Society warmly invite you as an engaging and knowledge-driven joint webinar aimed to fostering regional collaboration and advancing geotechnical engineering practices across South Asia. Today we have two distinguished speakers, Dr. Sanchitha Jayakody, Engineering-Based Landslide Mitigation for Settlement Development, and Dr. Sunil Poudyal, Forensic Investigation of a Catastrophic Embankment Collapse along the Meizhou Dapu Highway, China. This webinar will bring together professionals, researchers, and students to share insights, experiences, and innovative solutions in geotechnical engineering while strengthening the South Asian collaboration. Be part of the collaborative initiative and contribute to advancing geotechnical excellence in the region. Okay. Is there now Dr. Pathak? Is there
Vipul,
any?
can you share the slide? Okay.
Yeah, this is about the Nepal Geotechnical Society. It is established in 18 May 1994. Yeah, next. Yeah, we have, this is the 8th Executive Committee. We have running this institution right now for 2024 to 2026. Yeah, we are proud member Society of International Society for Soil Mechanics and Geotechnical Engineering, ISSMG, from 1995. We have about 600 plus domestic members and 22 international members. We are committed to international member till 50 in coming days. We have 9 honorary member, 80 plus youth member, and 28 institutional members. This is a NGS regular activities. We are doing monthly lecture programs, annual national seminar, 𝐿𝐤𝐴𝐬𝐴, and professional training, research training for youth, geohazard training, inter-society meeting and webinar, inter-Nepal webinar series, and a lot of publications. Youth program, geotechnical model competition, geohazard photography competition, thesis grant for students, and special discount in conference and programs. We completed some that type of activities. We completed international conference series of Nepal Geotechnical Society held in Kathmandu, Nepal in every 2 years. It started from 2023. And this is NGS Day celebration, 18th May. That is 31st NGS Day. And we are providing Lifetime Achievement Award, National Geotechnical Pride Award, Geotechnical Distribution Award, and Award for Special for Youth, Promising Young Researcher Award, Excellent Graduate Thesis Award, Best Undergraduate Technical Geotechnical Project. Okay. These are some activities with the community. Yeah, you can see in this slide. Yeah, next. Yeah, these are our publication, geohazard reconnaissance, and this is the for book first edition. This is the NGS efforts for global collaboration with Association of Geotechnical Societies, South Asia region. This is the for global collaboration, that is the training geohazard risk management workshop in 2024. Yeah, this is the also this is the global. This is you can see this is the 𝐿𝐤𝐴𝐬𝐴 second in Kathmandu. This is the pictures. Next, I think yeah, we are happy. Yeah. Okay, again, welcome to all panelists, attendees, and presenter for today's webinar. This is only from my side. Now back to you, Dr. Pathak.
Okay, thank you very much, Professor Acharya, for your valuable opening remarks together with the brief introduction of Nepal Geotechnical Society. Now, I would like to request Dr. Anil Joseph, now currently the president of our Indian Geotechnical Society and upcoming ISSMG Vice President, Asia Vice President, for your remarks. Over to you, Dr. Joseph.
Yeah, good evening all. It's a very big pleasure for me, first time after winning the election to the Vice President Asia, to be able to come and join my team of the strength of the South Asian Association of Geotechnical Societies and South Asian Collaboration for Geotechnical Excellence webinar. A great way to take it forward. I would like to thank Indraprasad Acharya and Sri Lal Sagabandhu, the presidents of the association, for taking the lead for organizing this webinar. Again, I am very thankful for my friends in Nepal as well as Sri Lanka, because the formation, the very idea of formation raised by Netha Prakash Bandari Sahab and Mandeep resulted in our coming together. And that has definitely made a big impact for us to move forward. And it is the root cause that we were able to win the election for the vice president post. So together we can make it happen was shown. So I'm also very happy that Mandeep Subedi was yesterday here in Kochi, along with Kalpana and San. So far there was a felicitation by the Indian Geotechnical Society Kochi chapter for their 18th years of formation and for honoring me for becoming the Vice President Asia. I'm very thankful for Mandeep and Kalpana for joining that in Cochin. So they will be joining this meeting from Cochin only, from my hometown. So thank you very much for that. And I know we have two wonderful speakers today, Sunil and Sanchitha, ready to deliver the talk. And on a very important aspects, which is affecting all of our countries in this region, I wish all the very best for the seminar. And Dundiraj Patak, it was a great pleasure listening to you, the way you organize the program. So let us have a great time, and all the people participants joining from NGS as well as SLGS. It's a great proud for me to be part of this meeting, and all the support. I would like to thank each and every one of you for the great support you have given us for winning the Vice Presidential election. Thank you all, and we should have a great seminar ahead, and together we can make a difference. Thank you.
Okay, thank you very much, Dr. Anil. Then your word is always inspiring to the Society of the South Asian Geotechnical Community. Thank you very much again. Now, without further delay, I would like to, it's the time to listen to invited speakers' presentation. And first distinguished speaker is Dr. Sanchitha Jayakody. And I would like briefly introduce about the Dr. Jayakody. He's the senior geotechnical engineer at the National Building Research Organization, Sri Lanka, with over 10 years of combined experience in industry and academia. He holds PhD in engineering from Kyoto University, Japan, and his research focus on modeling of geohazard using geotechnical centrifuge, testing and advanced finite element analysis. He's a corporate member of Institute of Engineers, Sri Lanka, and the member of International Society of Soil Mechanics and Geotechnical Engineering, and Sri Lankan Geotechnical Society, as well as Japanese Geotechnical Society. He has played a key role in major infrastructure projects in Sri Lanka and has led multidisciplinary teams in slope stabilization and rehabilitation initiatives. His expertise spans geotechnical investigation, foundation design, deep basement design, soft ground improvement, and risk-based landslide mitigation. He has published several papers in leading geotechnical journals and is committed to delivering practical, efficient, and resilient engineering solutions. Today, he's going to present on the topics engineering-based landslide mitigation for settlement development. With this introduction, I would like to pass the floor to Dr. Jayakody and request him for the presentation. Over to you, Dr. Jayakody, and you have about 20 minutes for the presentation.
Thank you very much, Dr. Patak, and very good evening, everyone, and of course, good morning, good afternoon. So, as wherever you are joining with us from today. So, first of all, let me share my screen. So you all can see it, right?
Yes. Now we expect in presentation mode.
Yes, sure.
Yeah, perfect. Thank you.
Yeah. So thank you everyone for joining with us, and also the Nepal Geotechnical Society and the Sri Lankan Geotechnical Society joining and jointly organizing this event. And so today's presentation title that we have I have proposed is the engineering-based landslide mitigation for settlement development. So I'm from Geotechnical Engineering Division, National Building Research Institute, Sri Lanka. So the topic that we have selected here, because as you all have heard or you all have seen that Sri Lanka has been hit by the cyclone Ditwa in last November, exactly like 4 months from today's, and it has brought unprecedented rainfall to the landslide prone area, especially that is the central part of the Sri Lanka. And the cyclone was walking around the island like for about 3-4 days, and unfortunately it has come inside, and then thereafterwards it flows very slowly through the country. So that has caused more than 1,400 major landslides. So that is like these tiny little red spots are the major landslide that we have identified through the satellite images after the event, and also that overlaps of the landslide hazard maps that NBRO has developed from their experience. And this event has caused more than 800 deaths due to the landslide, unfortunately. And NBRI being in Sri Lanka, so NBRI is the mandate and the focal institute in landslide management and landslide mitigations. So that time, NBR got huge responsibility to proactively get action, as well as, after the event also, we had to do major work. So before the event, NBR started giving early warnings to the general public. So we use our Met Department prediction data, as well as NBR has established about more than 500 rain gauges around the central highlands or the landslide prone area in Sri Lanka. And from their readings, the kind of very live readings, so we have passed our message to general public so that they can be in the safe places. However, unfortunately, as I mentioned earlier, that has caused more than 800 casualties because of this event. So talking about that event, so why we are going to do this landslide mitigation measures? So because this basically paralyzed our oil transportation. So that includes the major road system of Sri Lanka as well as the railway system. So to date also there are some railway lines that we are hardly trying to do the mitigation measures so that the railway transport can be resumed as usual. And also for the major roadway transportation, so right now we have done some temporary measures. So until we implement the permanent mitigation measures there. So talking about these mitigation measures, so right now, NBRI and RDA, the Road Development Authority of Sri Lanka, as well as the Sri Lanka Railways. So we have established a design office in NBRI to carry out this work. And so let's move on with the today's topic. So there are several type of landslide. So in this event, we have seen the rotational landslide, the translational landslide, the rock falls, earth flows, debris flows, and also there are some activated creep landslide as well. So understanding the type of landslide that has happened is the major thing that is going to give our effective mitigation measures. So giving that because the landslide is not a it does not have very generalized definition. So it can come with a different type of ways. So therefore, we need to understand what kind of a landslide it is, and our solution will be changed accordingly. And again, why do we need to talk about the risk? So because our designs or the engineering designs are basically to tackle this landslide risk. So as we all know, the risk is the measure of probability or the severity of an adverse effect to the life, health, or the environment. So that is basically quantified by using this equation, which is hazard into the exposure into the vulnerability. So if we want to reduce the landslide rate, so it is a very simple equation, which is either parameter we have to reduce. So if it is landslide hazard or the vulnerability or the exposure, we have to reduce at least one. So in that case, we follow this very systematic approach where we firstly analyze the risk and we assess it, and accordingly that we come up with the solutions for the mitigation measures. So we will follow this level of process. However, at the end, what we do is we will come to the risk management position. So there we choose, we adopt what is the most proper, more suitable, more sustainable, and also from this event, from the cyclone Ditwa, so the word that future-oriented mitigation measures. So somebody can question ask like, have you thought about any kind of a critical event like cyclone Ditwa in your designs? So that kind of a risk management that we have to do. And of course, we are proud to say that, I mean, many thanks goes to the our NBRI design team. So the designs or the mitigation measures that we have constructed all over the Sri Lanka in landslide prone areas has not been damaged, any of them. I mean, so many credit goes to all of them were part of that team from the last decade. So I am very proud to say that as well at this moment. So once we decide, so what component or what component of the risk that we are going to address, it would be the hazard or the vulnerability or the elements at risk. So depending on what kind of component that we are going to add, that we are going to tackle, our solution is going to be changed. So it could be the structural solution or it would be the non-structural solution. So the engineering comes in the structural part where if there is a stabilization or a control, so that is where our engineering part mainly involved in our design. So in this case, I'm going to talk about, I mean, with some case study that we had done in the, I mean, about some years ago. So that involves many of the things that we can discuss, maybe more, I mean, that may be the most, the general steps that everyone would follow in this arena of engineering. So if I come to the method or the methodology that at NBRI in Sri Lanka that we are following, so we follow these 5 basic steps in the landslide mitigation projects. So that start from the investigation, then we do the stability analysis. So that point we will get the as much as detail from the investigation, or if there is previous monitoring data. Likewise, so during the stability analysis, we may do the back analysis and we may confirm our assumptions, and then we move forward with the design. So for that one, we are taking the concept of factor of safety, and we have used these three different factor of safety levels to describe our solutions. And even though this shows that the factor of safety greater than 1 is we called as stable, but the following table shows here. So this I took from the Hong Kong Geo Guide. So that is a reference guide that we are always referring to in our designs. So there we compare the risk of life as well as the risk of economic risk. So depending on those conditions, so we need to have a minimum factor of safety values in our designs so that we can say it is okay to be implemented. And so once we are done with that step, we are going to do the selection part and the construction part. And for that one, I'm going to take the 𝐾𝐫𝐸 landslide, which is a creep landslide in Sri Lanka. So from the initial the surveying, the aerial photographs, we have identified there are 4 different types of landslide, and it is joined as a one block. But there are 4 different segregated landslides there. So even though that time the LiDAR images were not available, but recently we are extensively using LiDAR images interpretations for our landslide designs as well. From the basic investigation that we follow here is like we use, of course, the borehole data, and we do the resistivity surveys, because we can clearly understand the waterlogging areas such as shown in these figures, as well as we are now using the seismic survey so that we can establish the ground profile, combining and calibrating with the borehole investigation data. And this is the cross-sectional profile that we have established from our investigation data. As we can see, as a block A, block B, and the C and D likewise. And afterwards, what we do is we do the back analysis. That is basically to verify the obtained subsurface profile. And of course, since we all know that the borehole data might give the point-wise data, however, this is a kind of we have to generalize our borehole data. And so that so when we are developing our geotechnical model, we need to verify our assumption. So we first do the back analysis and establish all the soil properties and all the monitoring data if we have. So afterwards, so in that case, we mostly use the limit equilibrium and finite element analysis approach in our designing. So afterwards, what we have to do is to selection of what kind of structural measures that we are going to use. So in that case, most of the time, if we can do the hydrological methods, so we can genuinely reduce, we can deal with the root cause, so that is where removing the excess water from the soil, and so that the entire slope can be mitigated. So afterwards, if that is not helpful, we will go to the geometric methods. So that means basically changing the shape of the profile, so that can be like the soil removal from the headscarp, and then we can do some count embankment at the top of the area. And thereafter, the mechanical methods, even that is not also good. We can use the retaining structures, reinforcement like soil nailing or soil anchors in our works as well. So talking about the hydrological method, so why I wanted to highlight this fact is the water level fluctuations, and also how the factor of safety changes with the water level fluctuation is very nicely graphed in this analysis. So as you can see here, so when the groundwater level fluctuation, I mean, if it reaches the higher water table, you can clearly see the factor of safety is reaching less than 1. That means it has come to the unstable location. So if we can treat with this, we can clearly see if it is lower ground knot table, so the factor of safety will eventually be higher than greater than 1. So that is why we wanted to highlight that even at your home, or if you are living kind of in a hilly terrain, so if you are managing the surface and the groundwater, so you can increase the factor of safety or the risk, the lower risk, you can make it lower risk for the landslides. And again, the analysis that we have done, not only the surface strain, but also combining surface strain with the subsurface strain. So we sometimes call it as the horizontal drains. So we have done some analysis to show out, how the subsurface or the horizontal drains will be beneficial in these kind of critical situations when there is a high groundwater table effect is make cause the problems of engineering designs. And also I wanted to highlight these are some of the recent images that I have taken, and the left side figure is where we did some temporary measures for the some of the slopes in the Nuareli area, if you have heard of that. So we wanted to mitigate that roadside failure, and first of all what we did was we did some horizontal drains, so you can clearly see like how much water is flowing through this once we have done the horizontal drains at that point. So the right side figure shows when we were doing some mitigation measures in one of the major expressway project in Sri Lanka. So there you can see how much water pressure is there. So if basically we cannot stand in front of it. So that kind of a water pressure is there. So that is so much important to understand the impact of surface and subsurface water. So afterwards, as I mentioned, so there will be several mitigation measures that we can talk about. So, right, so we can deal with the hydrological conditions and also the earth removal work. Likewise, that is the changing the geometry. If it is not enough, we might add up some ground anchor, so soil nails. Likewise, as I told you, there are 4 different slip surface we had to deal. And also you can see, depending on what kind of mitigation measures, there will be a different factor of safety values we will get. However, the required factor of safety is 1.2. So then here comes the cost factor into our design, right? So if we design like all our everything, so if you put ground anchors, if you put everything, we can reach 1.4, but at that time, so there will be higher cost. So that is where again, so we have to that's why I started with the risk, right? So how much risk that we want to mitigate. So depending on that and the cost and the factor of safety condition, so we will select what would be the best combined countermeasures that we are going to put up in this particular site. And again, I want to highlight this one as well, because this was a very nice case that we come across. Because as when if we have visited the site, so the site is nicely cut into the nice benches with 1 to 1.5 angle, that is nearly 34 degrees angle. So in geometrically, if you do any kind of limit equilibrium analysis, so this would be a safer angle, right? So there will be no failure. But so the lack of geological or the geological understanding caused this failure. So this part is very weak soil, and so after they have cut this one, So the first rain spell, the slope got failed. So then afterwards, so we did the designing. So I just wanted to highlight. So we should not accept the solution or the whatever the output given by the any kind of software that you are using. So you have to use the engineering and the geotechnical, geological input, have they representing the site conditions carefully. So that is very important anyone to understand. Finally, so we use the combined solution, and the minimum requirement was set to 1.2. So we have reached 1.4. So we used the earth removal from the top part, and we used that soil to make a counterweight embankment at the bottom, and some of the ground anchors, as well as many horizontal drains with the drainage wells. So likewise, we have maintained a very nice solutions, and then we did the construction for it. So you can see the present condition of many of the items that we have designed. So this is the counterweight embankment we have constructed, and the drainage well. So you can see the horizontal drains, and we made a drainage well there, and the horizontal drains, and with the gabions at the top of the slope. And here is the surface drains we have constructed, and also the ground anchors as well. And afterwards, so we should not, because as far as I told you, so this was a creeping landslide, so we cannot completely forget about after we do the construction as well. So we did installed some inclinometers, and also some strain gauges, as well as some extensometers at the site as well, to do the monitoring and to make sure that the site is okay. And finally, I would like to wrap up my presentation with what we have surprised this time, because Ditwa caused many rain-induced rapid and long-traveling landslide in Sri Lanka. So it was not a very popular case in Sri Lanka, but this time there were many incidents. So however, we are trying to tackle this one, and we had some pilot projects. And what is the important thing here is, like, we might think that the settlement at the Toe area, so this distance is about 4-5 kilometers from the initiation point, right? And we think we are living in the very safe zone. But what happened was, like, so the flow path came and took an entire village with 50 houses from this debris flow. So right now at NBRI, so we have this kind of a very emerging threats. And yes, so our efforts is like to how are we going to treat these uh, threats. So then in that case, we are doing some analysis. So we use the ring shear testing. So that is what we call, what we can simulate geotechnically the high strain, and we can simulate the rapid and long traveling landslides, as well as we use LS rapid simulation, so that we can do some demarcate some flow paths as well. So I would like to wind up this section from that emerging threat that we are facing at NBRI and in Sri Lanka. And I would like to acknowledge the Sri Lankan Geotechnical Society and the Nepal Geotechnical Society and all the staff of NBRI for their hard working, especially during the last 4 months, and all our stakeholders, local and international collaborating agencies. And I would like to mention all the contributors of this presentation. Engineer Dr. Sri Karnavardhana, who is the Director General of NBRI, and Engineer Dr. Mihir Lakruan, my good friend at the Geotechnical Engineering Division NBRI, and also Professor Atula Kulatilaka, who is our consultant of many of the projects at NBRI. Thank you very much for this opportunity, and good luck.
Okay, thank you very much, Dr. Jayakody, for your very comprehensive and very insightful presentation. Yeah, I'm sure there are several questions to you, but we'll take all questions during Q&A session afterwards, after our next presentation. And I request all the participants to put your questions in Q&A box, indicating to whom you are going to ask the question. Thank you again. Now, I would like to request the second distinguished speakers today, Dr. Sunil Poudyal. He's from Nepal and he's the member of Nepal Geotechnical Society. And Dr. Sunil is currently a postdoctoral research fellow in the Department of Civil and Environmental Engineering at the Hong Kong University of Science and Technology. And he completed his PhD in civil engineering from 𝐻𝐾UST, that is Hong Kong University of Science and Technology, in 2025, specializing in geotechnical engineering. And he graduated with civil engineering and MSc in structural engineering from Institute of Engineering Pulcho campus of Tribhuvan University, Nepal in 2012 and 2015 respectively. And he was the recipient of a prestigious Hong Kong PhD fellowship scheme awarded by the Research Grant Council of Hong Kong in 2018. And he received the 2022 Hong Kong Institution of Engineers Best Geotechnical Paper Award. And he has actively participated in the leading international conference, presenting and his research work, mitigation of landslides and debris flow, using innovative technology, and published many papers. And he served as the General Secretary of the Association of Geohazard Professionals, Steep Creek and Debris Flow Subcommittee from 2019 to 2023. Today, he's going to present on forensic investigation of catastrophic embankment collapse along the Meizhou Dapu highway in China. With this introduction note, I would like to pass the floor to Dr. Poudyal for his presentation. Over to you, Dr. Poudyal. And you have also 20 minutes for your presentation.
Okay, thank you, Dr. Pathak. I hope you can hear me clearly and you can see my screen.
Yeah, yes, yeah, perfect.
Okay, so good evening, everyone, especially those from Nepal and Sri Lanka, and hello to anyone joining from some other time zones. I would like to first thank Nepal Geotechnical Society for inviting me to give this presentation on this joint webinar series for the South Asian collaboration on geotechnical excellence. The topic for my presentation today is the forensic investigation of a catastrophic embankment collapse along the Meizhou Dapu highway in Guangdong, China. This work was done under the auspices of the Center for Slope Safety project at the Hong Kong University of Science and Technology. Before I go into the technical details, I would like to acknowledge the support from my collaborators as well as my principal investigator, Professor 𝐶𝐻𝐫𝐚, and a number of different postdocs as well as students at the time who were instrumental in making this work a successful endeavor. So without their support, this work would have been of not such a great quality as it has turned out to be. So this is going to be the outline of my presentation for today. So I'll briefly introduce the Meizhou Dapu highway embankment collapse to you first, and then I will, based on that introduction, I will pose a couple of scientific questions that will that actually guided the forensic investigation. I will then delve into the details of the investigation approach and the results that we found, some key findings and the lessons learned for us. Despite the landslide being in China, this was a rainfall-induced landslide, and for our South Asian context, it seems this forensic investigation was a bit of an eye-opener. So let me begin. The Meizhou Dapu highway collapse occurred on 1st of May 2024 at 2:10 a.m. This is the coordinate of the event. So this was one of the largest or one of the deadliest calamity to occur as a roadside collapse in China in the past decade, resulting in 52 fatalities. So you can see the location on a Google map, on a Google plot over here. So this is what the highway embankment looked like in 2021, and in 2024 May 1st, on the night it collapsed at a section that measures around 18 meters, and then localized collapse of the highway slope, then run away into a debris flow kind of event. So I'll go into the details in the next couple of slides. This one was a tremendous event resulting in 52 fatalities with 30 people further injured. So the two key questions is how and why and how did this slope failure actually occur? And what did we learn from investigating the slope failure process? So these are the themes that I will be working on throughout the end of the presentation today. So the embankment failure in terms of some facts and figures, as you can see a clearer picture now. So there is a 18-meter wide section of the highway spanning across the width of the pavement that collapsed, causing a steep back scarp on this range. Then there was a retaining wall at the bottom of the slope that was then pushed further 100-meter downstream by the failed slope. What you can see also nearby the retaining wall location, the failed retaining wall location, is are the broken fragments of concrete facing that was on the highway slope, on the embankment slope rather, to prevent water from infiltrating. During the process of field investigation, I'm thankful to my colleagues who went there in their booths to collect soil samples. So we collected the soil sample from the embankment field itself, shown here in 4 stars, and then from the natural substrate ground in this location on the outside flank. So the collapse occurred at 2:10 a.m. This is the location at 24.49 latitude and 116.673 longitude, resulting in 52 fatalities, 30 injured. The length of the collapse embankment, I apologize, should be about 18 meters, not 26. And the landslide runout was more than 100 meters. The key forensic problem for this event was why did a locally failed road section turn into such a high mobility landslide? So this is something that we are trying to investigate. Professor Charles was one of the lead investigators in this event. He was mobilized by the Guangdong provincial government at the time. So we go into the technical details about the site. Once you look at the site hydrogeology, you can immediately see a upstream catchment right above the highway alignment and the slope. And unfortunately for this location, all of the drainage lines actually converge through the location of the failure. So there's a large catchment immediately upstream. The collapse site located along a drainage line that passed right through here. And then the lithology shows that the soil predominantly consisted of Cretaceous granite with varying levels of decomposition. The bedrock was moderately decomposed granite. Overlying it was a layer of highly decomposed granite, which is still classified as rock, and the surface lithology comprised of residual soil, that's the completely decomposed granite. In terms of the embankment fill that was present in the highway, it was also constructed by compacting the granitic fill from the cut slope above. Then, once knowing about the hydrogeology of the site, let's take a look at the rainfall distribution at the site in the month prior to the landslide. So on the left, we saw the hourly rainfall intensity in blue, and on the right is the cumulative rainfall. So throughout the entire month of April 2024, you can see a large number of rainfall events taking place. So the antecedent rainfall was quite prevalent, especially after 17th onwards. The entire area was quite soaked. This was an exceptionally wet season, April month for that location. And then on the early hours of 1st May, there was embankment collapse. The rain gates location was located approximately 20 kilometers away from the failure site at the town of Dapu. So that's how the highway name gets Meizhou Dapu Expressway. What we found was that the cumulative rainfall that occurred on the site was more than 700 mm over here. It accumulated during the month in April. And one interesting thing that we can see right at the end of the graph is that there is no high intensity rainfall during the embankment collapse on 1st of May. So there was a drizzle and there was light rain, but there wasn't a high intensity rainfall event that led to the collapse. So we have some interesting findings from the field investigation as well, especially if you take a look at the left-hand side. The collapsed sections of the pavement are over here, and the embankment fill looks essentially dry. It's in an unsaturated state, but 16 meter below the road surface level. If you take a look at the red highlighted area and then blown up, you can see that the water level at the toe of the landslide, essentially after the failure, the phreatic line passed right through the toe, and this is one of the borehole inaptly named like SLGS 15 that is provided in the report. So we can see the water level after the landslide at the toe. So this will come in handy later when we develop our numerical model and steady-state water condition to simulate the initial stages. So based on this field investigation and collection of data from news agencies, two scientific questions arise. One is, so where does the pore water that triggers slope failure come from? Because essentially this is a rainfall-induced landslide. The fill material is dry, so the pore water is unlikely from direct infiltration under heavy rainfall. So the hypothesis that we posed was it is most likely that the large catchment area right above the roads served as the source for the rainfall, and that the antecedent rainfall for the past 1 month significantly increased the permeability of the completely decomposed granitic soil that led to a rise in groundwater table. And the second hypothesis is, okay, this triggers a seepage-induced failure, and we can see that the soil has collapsed. However, why does the runout distance of the landslide actually reach 100 meters? That is another concerning thing for us. So when we take a look, there are two things that we can pose here. One concern is that, okay, how was the pore water pressure generated before the failure? And the second question that we have is, what was the friction angle of the soil? Because if it's traveling 100 meters, it's not at the peak values, but rather it's at, apologize, sorry, but it's rather at a residual angle. So to look more deeply into the first question, so where does the pore water that triggers the slope failure come from? We go into the investigation approach through a seepage analysis. This is the numerical cross-section in plane strain for the failed embankment. So we have simulated not only the section of the embankment that I'm showing here, but extended it up to a length of about 326 meters that incorporates the upstream catchment as well as the downstream runout zone. And the details of the rainfall infiltration through seepage boundary conditions are shown over here. It's also important to note that the road section along the pavement as well as the slope with the concrete facing was treated as a no-flow impermeable boundary layer. Then we carried out initial steady-state seepage analysis with a rainfall intensity of 0.1 mm per day, so that the design water level was at 88.2 meters in this borehole. as was found in the ground investigation report. And later, transient seepage analysis was carried out from the initial, from the steady state, after the steady state run, by inputting the rainfall conditions throughout the month of 1st April to 1st May. Now, there is one implicit assumption made in our rainfall infiltration boundary conditions, that 60% of rainfall infiltrates into the slope while only 40% contributes to surface runoff. Now, this assumption comes from a previous work published by Professor Charles back in 2001, which was again based on a Hong Kong Geotechnical Engineering Office report that conducted extensive field testing on Hong Kong slopes made of this completely decomposed granite. And then they found that at different infiltration rates, around 60% of the rainfall goes into the slope, yet 40% almost always goes out as a surface runoff. So that was one basis that how the numerical runs were carried out. These are the seepage analysis results in terms of pore pressure distribution along the slope. So we can see that the pore pressure in the embankment fill is essentially negative. So because of the impermeable boundary conditions, the suctions in the soil, in the fill soil, are essentially maintained throughout. We see the groundwater table at a phreatic line over here, traversing along the completely decomposed granite soil, and then the highly decomposed granite is under substantial pore pressure. Now, we are evaluating the stability of the slope at 3 different sections, section AA, section BB, and section CC, by taking a look at the pore pressure distribution. These are the input parameters into the model. At section AA, that is at the location of the embankment fill, where we saw the unsaturated dry soil standing nearly vertically, we see that the pore water pressure is indeed in the negative range. So a lot of suction is still preserved. And then a thin band of CDZ soil thereafter is saturated, followed by a linear increase in hydrostatic pressure for the SDZ soil. Similarly, if we go further downstream, where a significant thickness of the soil layer is now occupied by CDZ near the base, then we can see that essentially all of the suction in the fill is now destroyed, and then the CDZ is saturated with the hydrostatic pore pressure continuing downwards. Then at section C, where the SALD15 borehole was present, and after the failure, the free surface water was seen, we again see that the pore water pressure is essentially dropping from the CDZ layer downwards. These pore water pressure results are later used in carrying out a landslide dynamics model using SPH to estimate the runoff distance and see whether our proposed mechanism is actually valid or not. So from this plots, so what we are able to show is that, okay, the critical hydraulic gradient in terms of factor of safety, the factor of safety in terms of the hydraulic gradient, we find that the critical hydraulic gradient for this type of soil, where CDZ or the completely decomposed granite is classified as a sandy soil, its critical hydraulic gradient tends to be within 0.2 to 1. Now, the hydraulic gradient that we have observed between these 2 points, section A and section BB, is around 0.3. So this gives us a notion like, okay, the failure is induced by a hydraulic gradient and seepage induced failure. So the first question, where does the pore water come from and trigger failure, is essentially the cumulative seepage discharge of upslope rainwater through the CDZ soil layer. This can easily also be shown in terms of added vector plots on top. Then, with the first question gone, the water is going into the slope inside the CDZ. So how is it affecting the shear strength of the soil? So to do that, we now use the pore pressure distribution, and then we extract the effective stress. And we see that while the pore pressure is increasing, the effective stress is actually still quite high, especially at section AA because of suction preserved in the fill soil. the effective stresses are pretty high, and only when we reach the groundwater surface that the effective stress shows a transient reduction, while down in the SDG soil, the effective stress again is following in a lithostatic manner. In section BB and CC, we see a similar increasing trend of effective stress. It's still a nominally high effective stress. So what does this suggest is that liquefaction of the soil is quite unlikely. So failure by static liquefaction is not the way the slope failed by loss of shear strength. Rather, it was the hydraulic gradient that exceeded or reached the critical hydraulic gradient and exited downstream of the retaining wall. So perhaps the hypothesis that we proposed earlier now seems quite correct in terms of where the water came from and how the slope was triggered. So initially, we see that a landslide is triggered by seabed force. Now, to investigate what is happening in terms of the long run out, we are now going to look into the ring shear tests. So why does the run-out distance of landslide reach nearly 100 meters? We wanted to understand the shear strength properties at large deformation, and we did some basic soil engineering properties. So we only took soil material finer than 2 mm for the ring shear test based on the limitations of the device. So these are some of the basic soil properties. And the investigation was carried out in a ICL undrained ring shear device. I saw that Dr. Jayakody in his earlier presentation showed one slide of a similar equipment that they were using. Essentially, annular soil samples are prepared inside the space and then sheared to large enough displacement to ensure that residual states or steady states are achieved. So these pictures simply show the configuration of the device and the ensuing output at the end. Now, looking a little bit deeper into the shear stress profiles. So when we look at the effective stress plot over here, for the left-hand side, we see the series soils that we tested at 150 kPa, 300 kPa, and 500 kPa. And for decomposed granitic soil, we also borrowed we see that the effective, when we do shear the soil, all of the series soils undergo strain softening with rapid loss of shear strength. And in the case of fill soil, the behavior is quite different. It does indeed undergo initial peak followed by a softening, but near the end, there is a phase transformation with soil hardening behavior. So we see that in saturated undrained ring shear tests, strain softening is common in both CDG and fill, but the deviation comes up that in the case of fill soil, when the confining pressure is 200 kPa, the initial strain softening behavior then transitions into a phase transformation and a strain hardening response. And it's important to note that shearing was done in a rather rapid rate of 5 millimeters per second rather than the conventional 0.024 millimeters per minute. Simply because we were trying to investigate the failure mechanisms and of a large of an exceptionally mobile landslide. So that's why a higher shear rate was adopted in this study, and this has also been shown by Professor Sasa's group in Kyoto about the effects of shear rate. So those were the basis why we chose a rather faster shearing rate in our experiments. Now that was shear stress in the effective stress plane. Now, when we take a look at shear stress in the displacement or shear strain profile, then we can see a clearer picture of how the increase in shearing led to severe softening of the series soil with residual friction angles reaching as low as 8 degrees for lower confining stresses of 150 kPa. Yet when the confining stress was slightly higher to 300 and 500 kPa, then the residual friction angle also started to increase slightly. For our case, based on the investigated failure depth of the landslide, we are going to adopt the residual friction angle around 8 to 10 degrees with 16 meters of failure depth identified from the site. Now, if we consider the results of severe stress strain softening in the case of CDZ, and now we directly compare that with the fill soil, we see that yes, there is a strain softening response to even up to a strain of up to 600%. But when we go beyond to strain of about 1000%, we get residual friction angle increasing. I will get to the details of this in the next slides. And in computing the strains for this soil, we have used the initial sample height of 50 mm to calculate the strain in terms of the in terms of the displacement induced on the soil. So what we find is CDZ has a very low friction residual friction angle of around 8 to 10 degrees, but fill soil has essentially phase transformation behavior, so the residual friction angle will be either equal to or even higher than the peak. Now, after the ring shear testing, so when we sheared it to about 500 mm and we stopped the testing, this is for the CDZ soil. So as a visual aid to the side, the shear plane is located right at the top of the rubber membrane seen over here, and the shear band extends to this depth, where we can see a lot of fine particles located within the shear band, and a lot of the coarser materials are located above the shear band. The CDZ soil essentially is a silty sand, so it looks quite granular. And what we see is that within the shear band of the CDZ, grain crushing has led to a reduction in the particle size. Then we compare the same for the fill soil, and what we find is, in addition to the fine particles, we find some coarser particles within the shear band for the CDZ. So the coastal particles may have contributed to the phase transformation of the soil from strain softening to strain hardening behavior, even at strains exceeding 600%. So now we have two clear results. One, where the water came from. Next, okay, the low friction angle of the CDZ is the likely culprit where the failure or the trigger occurred. So the gun is locked and loaded. Now, to understand whether our assumed friction or our experimentally evaluated friction angles are actually going to produce reasonable results, we carried out landslide dynamic simulation using in-house SPH code. So what you see here is a cross-section of the hill slope that was then simplified and modeled for SPH simulation. So we modeled, in this case, everything as a Drucker-Prager material with a cohesion of 2 kPa for numerical stability and a friction angle of 10 degree, assuming a basal friction angle. And as I noted earlier, from the CPS analysis, we extracted the pore water pressure at the base. We then input that pore water pressure profile over here, right before the simulation starts, as a body force, or rather a surface traction at the boundary, so that we can get the effects of pore water pressure increase during initiation. Note that the rest of the simulation is conducted as a total stress simulation. So when you see here with 10 degree friction angle and a given cohesion, so this we try to model the ground surface after failure, and then based on the location of the initial position of the retaining wall and that after failure, we find a reasonable slide to flow mechanism. So the post-failure ground surface that is captured by the SPH numerical model, especially for the downstream end, looks much more reasonable with what was observed in the field for 10 degree of friction angle. So is this okay? We then carried out a number of parametric studies with the same geometry by increasing the friction angle. Maybe the friction angle of the soil is not that large. So what happens in those cases? If we simulate with 15, 20, and 25 degrees of friction angle, then we can see that the landslide dynamics are completely different, and that the landslide mobility severely reduces with increasing friction angle. With that we see that, okay, the 10-degree friction angle shows a reasonable landslide dynamics to what is observed in the field. But the other values are essentially overestimating the frictional behavior of the soil. We then go on to compare the final deposition profile with the measured one, and we see that the residual friction angle of 10 degrees has a runout distance of around 93 meters. This is essentially this essentially matches with almost around 100 meters of the retaining wall distance that has traveled after failure. But in the case of 25 degrees, it's only 14 meters of distance. 20 degrees has 26 meters of runout distance. So these are not quite reasonable. So we can now, at the end, conclude that for the question number 2, why does the runout distance of the landslide reach nearly 100 meters? The answer is the lower residual friction angle of CDZ from very large strains leading to severe strain softening. So what are the key findings and lessons learned from this forensic investigation? 1, the cumulative rainfall from the antecedent rainfall in upslope catchment area was the source of water that triggered embankment collapse. And then secondly, the high water pressure combined with low residual friction angle of the CDZ allowed the collapsed embankment to flow nearly 100 meters downstream. If we combine both of these eventualities, then the failure mechanism is characterized as a slide to flow type failure. Then, what are the lessons learned that we can carry from what we observed in the Meizhou Dapu highway collapse for our conditions in region? One is the engineering lessons that are transferable to monsoon affected regions is if we only assess the peak stability and surface rainfall infiltration, we may actually miss the real hazard. That's one of the key findings from this study. What I meant is we need to examine the catchment controls of subsurface flow in hilly terrain. Rainfall infiltration directly from the surface may not be the main driver of landslide. Secondly, if we need to rigorously incorporate long duration but relatively low intensity antecedent rainfall in design checks. This failure occurred not during or immediately after an intense rainfall spell that we would generally see for shallow landslides, but it occurred after a long duration of relatively low intensity antecedent rainfall over a span of 1 month. So with changing climate, that may be another thing that we have to check out. Finally, and what this findings shows, as well as I echo what Dr. Jayakody presented earlier as well. Design of a drainage system as a primary stabilization measure is of utmost importance for landslide mitigation, especially in resource-strapped regions like ours. So this has been the end of my presentation. And the next thing that I want to address is check for the residual strength control sequence and not just a factor of safety at initiation, as Dr. Jayakody also alluded in one of his presentations, with the exceptionally mobile debris flows taking place in Sri Lanka. Although you are on a flatter terrain, perhaps residual strength based simulations are now needed when we want to do landslide mapping, risk assessment, and journings. Thank you for listening. If you have any questions.
Okay, thank you very much, Dr. Sunil, for your very detailed presentation, and I hope audience have found to be very informative. Thank you again. I request to all participants to put your question in Q&A box. I think I saw already questions is there in Q&A box, and our speakers will respond. You can see in the Q&A box and respond right now shortly because we are already running out the time. Around 5 to 7 minutes, we can right now respond from our speakers. If not possible, we also consolidate all these questions and send our speaker for their response later and then send to you all. Please, you can look in Q&A and many of our participants and you indicating to whom. First, you can, Dr. Jayakody, start to answer a couple of questions right now. Dr. Sanchitha, over to you.
Yeah, I think I just opened the Q&A section. So one question says, how did you balance between structural mitigation measures like retaining systems and unstructured approaches like land use, especially in resource constraint settings? Actually, in Sri Lankan conditions, so what we are doing here is like, so if there is a critical infrastructure, as at the start of the presentation, I showed that some of our A-class roads and our railway transportation has majorly damaged. So in that kind of a case, we actually had to use the structural measures, right? And also like sometimes in Sri Lanka, it's like the settlements or the people are living in kind of unstructured and also very dense settlements are there, which is not possible to relocate, which is very impractical. So in such cases also, right now we are dealing with such conditions like there are some housing units has been already constructed, but without thinking about these kind of measures and also the in unstable conditions. So they are also right now we are going to do some mitigation measures in such establishments as well. However, the problem we are facing or we are trying to disseminate the message like that the living with landslide concept. So that is right. So we have to give them the proper education and like how are you going to mitigate the establish your surroundings, I mean minimizing the risk. In that case, actually, as I already explained, the dealing with the hydrological conditions, having proper drainage and everything would be very beneficial for them. So in that is the mostly the uh, the structural measures that we are giving, but the land use planning is very important, but to be honest that it is very hard and because we have to deal in the social problems, so that kind of end. So those element risk analysis is of course as part of our resettlement program. Our NBRI group is doing very much hard work on identifying the sources of lands and how do they going to do such land use planning in such conditions as well. So yeah, I hope that I answer your question.
I think thank you very much, Dr. Jayakody, because we have already running out of time. Then
Yeah,
I will take
sorry for
one
taking.
question further, Dr. Sunil, and then we consolidate all the questions and send to you both speakers and share with
Yeah,
all
yeah, sure, sure.
participants later. Yeah, so
Okay,
Dr. Sunil, for
great.
you can take one question right now and
Okay, I think I was partly
shortly.
answering Ashish Pastala's question there. So yes, we did measure the soil water characteristic curve or the soil water retention curve for this soil. We found that this CDZ soils, especially the CDZ soil, was very similar to that in Hong Kong as well. So the granulometry was essentially very similar, and we compared the SWCC. It fits the Van Genischen model similar to what we had for the Hong Kong soils for more than 20 years now. We simply used those measurements and then input them into the CW software for simulation. So that was, I think that's for your question. I think I see one more question from Neelam about heavy embankments in mountainous regions often involve complex interactions between fill material, foundation soils, and drainage. So in this regard, in what our investigation found is that in the Meizhou Dapu highway case, there was a clear lack of consideration for the hydrogeology of the site because of the fractured Cretaceous granite, the levels of decomposition there were quite variable. So what happened was, where the exact location where the failure occurred happened to be at a cross section of two drainage lines. So at an exceptionally large antecedent rainfall over the 1 month, the cumulative discharge was very high through that area. So I suspect that may not have been considered quite well in the design. So, and history from the site also shows that there was some slope movement beforehand, and they had some issues related with groundwater control at that location. So they included the concrete facing in 2024, and then in 2023, sorry, and in 2024, the slope unfortunately failed. So if you are able to track the slope surface features as well,
Sorry
that
for
seems critical.
Dr. Sunil, I'm sorry for interrupting you, because we will collect consolidate all these questions, and we encourage to all these esteemed participants still type your questions in Q&A box. We gathered all the questions and sent to our speakers. Right now we are I would like to proceed the program. Thank you very much for both speakers for your outstanding presentation. Now I would like to invite Dr. Mandeep Trivedi, the chair of Geomandu 2027, with the 11th 𝐴𝐻𝐺C and the first South Asian Conference in Geotechnics, which is going to be held in 17 to 19 March of 2027. And Dr. Mandeep is also immediate past president of Nepal Geotechnical Society. And of course, because of his hard work and the continuous engagement with both like senior and young geotechnical engineers, the NGS attained a new height in a very short time. And thank you very much, Dr. Mandeep, for your great contribution to bring the NGS in today's position. Having said that, I would like to request to Dr. Mandeep to invite our participant in the next Geomandu, and over to you. I think you have 5 minutes for your talk.
Thank you, Dr. Rindira Pathak sir. Hello, everyone, especially Dr. Indra Prasad Tare sir, Dr. Anil Joseph sir, and Sahabandhu sir, Srilal Sahabandhu sir. Today I am at Kochi, and I am as a part of the 18th anniversary program of IGS Indian Geotech Society co-chapter, and the facilitation of Dr. Anil Joseph for his contribution on the geotechnical fertility of India, and also for the South Asia region, and also he's being the elected as the Vice President of ISSMG Asia. Congratulations, Dr. Anil sir. Now let's enter to my topic. Geomandu is the conference series of Nepal Geotech Society to be organized at Kathmandu in every 2 years, and this time this conference is being jointly organized with the 𝐴𝐻𝐺CE and South Asian Conference of Geotechnics. And the abstract, the submission of abstract will end at 30 April. But to make the participants great, we will extend for the international participants for some time also. And the conference will be at 17 to 19 March 2027. And till date, we have obtained 138 abstracts, and we aim to obtain the abstract more than 130 up to 400 abstracts. And among them, I think we will have 200 papers in Geomandu 2027. Till date, 17 countries we have obtained the abstract from 17 countries. And for the 𝐴𝐻𝐺C, we need the participants from all the Asian countries. We asked the nominations, and from 26 Asian country society, we have obtained only from 13 societies, and I think we will obtain the other nominees in coming days also. We have also obtained the papers, nominees from Sri Lanka, and 3 nominees from Sri Lanka, and these are the names. And for this, to know, this is also the conference of South Asian Association of Geotechnical Societies of South Asia, and in this conference, as a part of this conference, we will do a panel discussion, and in that panel discussion we will discuss about the common issues of our region. And beyond the conferences, papers, and also the things, you will enjoy 𝐿GeoMandu 2027 very much. You can have enjoy the land up from 60 meters from sea level, just like in the Kochi. I think Kochi in the sea level area, but in the 60 meters sea level to the highest peak of the world. And we can also have the beautiful city, see the beautiful city in a very short time also. And to know how our 𝐿GeoMandu were going, in first 𝐿GeoMandu we had 300 participants, and among them 30 were the delegates from international societies. In 𝐿GeoMandu second, which was held in 2024, we had around 500 participants, and 172 were international delegates, and we had presented 160 papers at the second 𝐿GeoMandu, and these are the proceedings which that were published in second 𝐿GeoMandu. We have four volumes for it, and which were published in the Springer lecture notes in civil engineering. And these are some photographs of 𝐿GeoMandu 2023, and this is the photograph of 𝐿GeoMandu 2024, and this is also the photograph of 2024, and this is the video that we had during 2024.
र यो एरियातिर हजुरहरूले घर बनाउँदै हुन्छ भने चाहिँ तपाईले लाइम र सिमेन्ट स्टेबलाइजेसन चाहिँ एकचोटि गर्नु होला।
Okay, this time this conference will be more special because we will have a LARAM course as a pre-conference event with the coordination of IIT Indore and also the Institute of Engineering IOE Poudyal campus, and also post-conference activity will be also good. So I would like to invite all the people from many people, many researchers, and the professionals from Sri Lanka too. And please, Sarbandu sir, help to reach about the 𝐿GeoMandu to the people of Sri Lanka. And I think our problems are also our solution, our issues are common. So we'll discuss on the 𝐿GeoMandu. Thanks for for listening me. Okay, thank you. Bye.
Okay, thank you very much, Dr. Mandeep, for your valuable remarks and with highlight of the GeoMandu 27th and with the 11th AOIGC and first side. Now we are the end of today's program, and I would like to request the engineer 𝐾𝐬𝐴𝐵𝐴, the president of Sri Lankan Geotechnical Society, to conclude the program with a brief introduction to Sri Lankan Geotechnical Society with the closing remarks. Now this is my job is now over. It's already almost 3, 4, 5 minutes we run by the program, delay by the program. Then now I will request to Engineer 𝐴𝐵𝐴 for your closing remarks. Over to you.
Thank you. We are very pleased that Nepal Geotechnical Society has initiated to have this kind of webinar in collaboration with Sri Lankan Geotechnical Society. That is actually the first webinar series we have started with Nepal. Before that, we had a few with Indian Geotechnical Society initiated by Indian Geotechnical Society, especially by Dr. Anil Joseph. And also, I would like to give my congratulations to Dr. Anil Joseph for electing him as the Vice President of Asia. I think we can go a long journey with his leadership for the next 3 years. And I think the South Asian community should be very proud about his nomination, his election. And also we must get together and work together to achieve our goals. You asked to me give some conclusion remarks. I would like to say that this webinar was very good, and we had two very young, prominent geotechnical engineers from Sri Lanka, Sanchitha, and from Nepal, Dr. Sunil, and from Sri Lanka, Dr. Sanchitha, and they did a great job, and they actually had a case study about Sri Lankan situation as well as Nepal situation. I think we both have similar situations when we come to the geology of our soil. Maybe they are a little different, but it is almost same. I think all South Asian countries, we have common problems, and also we have common soil profiles. And that may be the great thing. We have to get together and do studies and investigations and publish our findings, especially in these coming conferences. That's why I'm also joining with Dr. Mandeep to invite all of you for the conferences we are going to organize in South Asian countries. We have 27. We have a big conference in GeoMandu conference in Kathmandu. I have participated in that conference about 2 years back. It was a great and it was a very knowledge sharing event. And similarly, I have participated in Goa, Asian Geotechnical Conference. That also a great event. And this year we will have in Sri Lanka, we will have a international conference. And I think everybody is aware about it. And I can just share my screen. I don't know whether it is possible. Yes. Yeah, this is the, let me see. Yeah, this is this is the our second flyer published, and we are up to publish another brochure. And I guess I invite all of our South Asian colleagues to participate. Already we got about over 100 abstract, and I think we have come to the full paper stage. And I think we are doing the review at the moment. I think we hope at least 100 papers will be published in this conference. And I'm very thankful to Dr. Anil. He has initiated, and we have many conference papers from India. Still, you can send your papers. We will even the deadlines are over. We can accommodate those things, and I am sure you will make a benefit out of this conference. We have the keynote speaker, Professor 𝐷𝐵𝐸𝐺𝐻, and then our Vice President, Professor 𝐼𝐿𝐵𝐺𝐻, and then Dr. Richard Kelly, then Professor Jayantha Kodikara, then our President, ISMG President, Dr. Mark Bulloss. Then we have Professor Gopal Madhubashi. And with that invitation, I again appreciate, and I will thank everybody who has participated in this webinar. And I am sure we will have more seminars, more webinars in this nature to share our knowledge. And that is a very cheap and very cost-effective method of doing it, rather than having physical seminars. And we all can join. And my suggestion is to have at least one conference, one webinar in each month. Then we can share a lot of things, lot of geotechnical information and knowledge with our people in the region. Thank you very much, and good night.
Okay, thank you very much, sir. Now the program is